this module we will conclude our study of transmission lines by looking at its response to pulse input and then also consider the capacitive termination, which is something that you would find in most transmission line problems, okay, where the load happens to be not just a pure resistor but combination of resistor and capacitor. For this course we will consider only a pure reactive termination such as a capacitor. Okay. So let us begin by first considering the pulse response of the transmission line. So what we actually mean here is that we will launch pulse on transmission lines and then we will try to find out what is the voltage at the load, whether the pulse would be reproduced faithfully or whether the pulse actually gets distorted, okay, because of the reflection problem, not matching at the load and not matching at the source side. Okay. So the problem that we will consider will involve launching a certain pulse. Okay, let us say the pulse has an amplitude of V0, and for our convenience sake we can consider this pulse to be starting at 0 and being non-zero until a duration of t seconds. That is, the pulse essentially is there for a duration of t seconds, and we want to see what happens when such a pulse source is connected to a transmission line. As I said, in many digital circuits you have one digital device driving another digital device. This entire thing in between is what is called as an interconnect, and in high speed digital designs this interconnect, IC interconnects, actually has to be modeled as a transmission line. Okay. This transmission line has a certain length and therefore there is a certain propagation delay TD associated with this transmission line, and although we have shown and we will be using only resistive loads and resistive sources, the slightly more realistic representation of this one would actually be a complex load, which will have both a resistor and a capacitor, and similarly you will have mostly a capacitor plus some resistor either in series or in parallel being driven. Okay. So the load is not just pure resistor and source resistance is also not just pure resistor. Okay. So there are these reactive elements, and how the pulse would actually propagate in this realistic scenario is something that you will have to do it when you study this in further detail. For this particular module and for this course we will assume that for the pulses to be propagated on the transmission line, both the source as well as the load terminations are resistive. Okay. So we do not consider the complications that would arise because of the capacitive reactances also being found at the load or the source side. So for us the source will be represented by a resistor, okay, has some resistance Rs, and then there is a pulse source which we are connecting. Then there is a transmission line which basically is assumed to be lossless and has a characteristic impedance of R0 or Z0 and has a propagation delay, one side propagation delay of Td, which is given by L by U, and U is the phase velocity, or U or UP is the phase velocity of the waves that we are considering. Okay. So this will be terminated by a certain load resistor RL, which again is assumed to be real. Now how do we actually start this problem? I mean, we have already seen how the transmission line would carry a step voltage from the source side to the load side, right. So there would be multiple reflections involved when gamma L, the reflection coefficient at the load side, is not equal to 0, or when gamma G is also not equal to 0. So you actually have multiple reflections, which means that the voltage that you get at the load side would not be a pure step waveform, but rather it would be a waveform which would tend to be some value. It would be oscillatory or it would be damped, but it would not be exactly a step waveform. So in other words, it is actually getting distorted, the wave is getting distorted as it propagates through this particular system. I mean, as not propagated, but because of the multiple reflections. Okay. So that was for the step response. Now how are we going to analyze the response, or how do we understand the pulse propagation on the transmission line? Well, you remember from your signals and systems courses, probably that is what we call them, this pulse source can actually be broken up into two step waveforms. How? You have one step which I am representing here by a red line, okay, which has an amplitude of V0 and is switched on at t equal to 0, right. Then we also have another step waveform which does not appear until t equal to t, capital T, but then at that point the pulse actually has an amplitude of minus V0. So this pulse has an amplitude of plus V0, this negative step has an amplitude of minus V0 and it would be turned on at this time t. What would happen? Between 0 to t, the capital T, there is only one step waveform, therefore the voltage actually is equal to the original pulse voltage. Whereas after t, that is after capital T, where the pulse is supposed to be going to 0, it does indeed go to 0. If you consider this as a sum of two opposite amplitude, right, they are equal amplitude but they are opposite in sign, right, and then you add them up. So at every point t greater than capital T, what you get is essentially 0, right. So if you add these two up, you will, what you get here is a 0 here, okay, and then it would continue all the way. So the lesson of this one was that a pulse can actually be thought of as sum of two step waveforms of equal amplitude and switching on after a certain delay, right. The delay is the pulse duration t, okay. So this is the pulse duration t. Now this must make our life very easy because we already know how to solve for one step waveform on the transmission line, and because this problem is essentially linear, you know, the transmission line is linear, this can be analyzed using superposition in the sense that you establish the response of the transmission line circuit because of one step waveform which is turned on at t equal to 0, and then you examine the effect of the same circuit for step that is actually starting at t equal to capital T and has an amplitude of minus V0, and both of these problems can be solved by appropriately modifying the lattice diagram, okay. So let us actually try out on a numerical example over here. So assume that gamma L happens to be 1 by 3 and gamma G happens to be minus 1 by 3 for some combination of loads that are not really important for us, or if the load values and the characteristic impedance of the transmission line as well as the generator impedance RS is given, you can actually calculate these values, okay. So they could, you can calculate, and then you have, what you will be using is these equations, right. So I have actually given you that equation. So I mean given you the values, gamma L is 1 by 3, gamma G is minus 1 by 3. So now you can actually imagine, even before something would happen, that there would be, if the original step waveform is applied, then there would be an oscillations happening, right, because in one way you are going, then when you come back to the generator side, the voltage has to be negative of whatever that has come through, right. So there would be certain oscillations, and this would correspond to the underdamped situation that we saw in the last module, okay. Alright, so let us also assume that the pulse lasts for about say 0.1 nanoseconds, okay, in one case, and then we will extend that to 0.8 nanoseconds in the second case. So for us the duration here at this time is 0.1 nanosecond. The amplitude of the pulse, you know, is 12 volts. These are chosen so that, you know, further calculations are slightly easy. Now the only thing that you have to understand is what is the time delay of the transmission line, okay. So for the time delay of the transmission line, if it is specified that the length of the transmission line is 0.9 meters, okay, and u is specified as approximately the value of c, free space propagation of light, which is 3 into 10 to the power 8 meter per second, then you can calculate the one way propagation delay Td as 0.3 nanoseconds, right. Now this is interesting, the pulse itself is only 0.1 nanoseconds, the transmission line has a delay of 0.3 nanoseconds. What would you think would happen? Spend few minutes on this problem thinking over what would happen. The essential idea is that you are launching a pulse whose duration happens to be much smaller than the propagation constant, right, I mean propagation delay. So this pulse would propagate, right, so this pulse would propagate and arrive at the load side at 0.3 nanoseconds after the pulse. So the entire pulse is available from 0.3 to, so since the duration of this one is 0.1 nanosecond, the pulse is available from 0.3 to 0.4 nanosecond at the load side, at which point it further gets reflected and would arrive back at the source at 0.6 nanoseconds and lasts until 0.7 nanoseconds, right. So between that there is nothing coming in here because the pulse has already completely come to the load side. So the load would get excited only from 0.3 to 0.4 nanosecond, and then it will wait for the next bit of reflected pulse to come through. The next bit of reflected pulse will come at 0.6 plus 0.3, which is 0.9 nanoseconds, and lasts until 1 nanoseconds, because it is 1 nanosecond is the duration, so it lasts until 0.9. So at this point you might imagine, because there is a negative thing out there and there is this one, the voltage that would come back would have a value that would be lesser compared to the original one. So you would actually have something that would look like having a negative value here, because this is a negative, because gamma g is negative in this case. If gamma g were to be positive, then this pulse amplitude would be positive. So this pulse would start at 0.9 and last until 1 nanosecond. So if you calibrate all your time axis in terms of nanoseconds, then this is how you would expect, even before doing any of the calculations, this is how you would expect the voltage to appear at the load side. Let us actually verify that this conclusion is correct by drawing the lattice diagram. Okay. So to draw the lattice diagram, remember what we need to do. This is z equal to 0 and this is z equal to L. This is the load side and this is the source or the generator or the driving side. Okay. The time axis is still along this one. Okay. All calibrated in terms of nanoseconds. Okay. And now let me first write down this 0.1, 0.2. Let me write down the scale here. Okay. Otherwise I will not be able to draw this one, fit all the time, or at least the time that is significant for us in this one. So you have 0.8, 0.9 and 1. So this is probably sufficient for us. If you want, you can also go to 1.1, but this is probably sufficient for us, because we do expect by our previous understanding that you will have two pulses, one at 0.3 and one at 0.9 and lasting until 1 second. Thereafter there will be something else at 1.6, but that is way too long time that we need not look at that part. Okay. So let's also write down what is gamma L. Gamma L is 1 by 3. Let's also write down what is gamma G. Gamma G is minus 1 by 3. Okay. Now let us launch a pulse. But you know that between times from 0 to 0.1 you actually have a pulse of amplitude 12 volt, but that 12 volt will not be the one that is actually launched on the transmission line, right. So you imagine that there is a step waveform here which will then continue to be there, and then at this point this will be the negative step. So you simply propagate this one. Okay. So there will be two steps that you need to propagate, one with a positive value, the other one with a negative value. I will try to write down both of them with two different colors so that we can actually see that one. What is the initial pulse amplitude that is launched? Well, the load does not yet appear at the transmission line at the source side when you close and apply the switch, apply the pulse. So initially it is only this R0 of the transmission line that is relevant to us, and then there is certain RG over here, and then a 12 volt step is applied, right. So what is R0? Let us assume that, or let us look at this one. So R0 is given to be 50 ohms, from which you can actually calculate what is RG, or you don't have to calculate that one, that would be 25 ohms. Okay. So here we don't have a match over here, and you can actually see that gamma G will be minus 1 by 3. Similarly, RL is 100 ohms. You could have obtained this value from knowing what is gamma L. Alright. So now let us launch one pulse. Okay. What is the initial pulse amplitude that we need to launch? So V1 plus will be divided between the R0 and RG, and the voltage appearing across R0 is 50 by 50 plus 25 into 12. This is nothing but 2/3 of 12, and this is 8 volts. So initially an 8 volt step waveform is launched on the transmission line, and it begins to propagate, and it will reach the load end, okay, at 0.3 nanoseconds. Okay. So here you have 8 volt pulse that is being launched on the transmission line and arriving at 0.3. As soon as this step arrives, there would be a reflection of the step. Okay. So the step value gets reflected, and what would be the reflected value? Reflected value is V1 minus, which is again gamma L, which is the reflection coefficient here, times whatever the initial value V1 plus that we obtained. Gamma L happens to be 1 by 3, V1 plus is 8, therefore this is 8 by 3 volts that gets reflected. So this 8 by 3 volts is approximately 2.66 volts. You can use a calculator to check whether this value is correct or not. So once you have done that one, now you begin to propagate this reflected value, right. So what is the value that is getting reflected, and when will it arrive? It will arrive at the source side at 0.6 nanoseconds. So this is how the reflected wave would travel. Now at this point immediately the wave gets reflected and it would arrive at 0.9 nanoseconds, right. What is the value that is reflected here. So this is 2.66 volts or 8 by 3 volts, and the value that goes over here will be 8 by 3 into minus 1 by 3, which is minus 8 by 9 volts. So it's actually negative and it is very, very small. So this is about, I mean, it's a very small number, right? So it's minus 8 by 9 volts. Okay. So I hope I have got all the numbers correct over here. And again, once you get a value here, it gets again reflected, but we don't have to calculate that one. The amount that gets reflected, I mean, we don't have to propagate this one, but the amount that gets reflected is minus 8 by 9 into 1 by 3, which is minus 8 by 27. So this is minus 8 by 27 volts. This is how the first step would behave. Now this is not the end of the story. We need the second step, and the second step begins at 0.1 nanoseconds, but it has an amplitude of minus 12 volt, right? So all you have to do is basically change these values from plus to minus as you propagate the second step. Okay, so pick a different color, and then when would this arrive? The step, negative step starting at 0.1 nanoseconds would arrive at 0.4 nanoseconds, right? So it would arrive at 0.4 nanoseconds, and what is the value? Minus 8 volt gets reflected. So what would be the value? Minus 8 into 1 by 3, which is minus 2.66. Where would this arrive? So this was at 0.4 nanoseconds. Okay, so 0.4 plus 0.3 is 0.7, so it should arrive at this point, and at this point the reflected voltage is minus 2.66 volts. Again the voltage gets reflected and it would arrive at 1 nanosecond, right, and then get further reflected. So what would be the value here? It is minus 8 by 3 multiplied by minus 1 by 3, that would be plus 8 by 9. So this would be plus 8 by 9, and then this fellow would be 8 by 27 volts. Okay, so it is actually comforting for us because this step would continue to have a value of minus 8 by 7, right, for all the time, but this step will have a value of 8 by 27. Therefore after 1 nanosecond the sum of these two will be equal to 0. Now if you were to draw the voltage waveform at the load side, this is what you are going to observe. So let us call this as 0.3 nanosecond, and it would be 0.4 here, this is 0. So let me calibrate t in terms of nanoseconds. What would be the pulse value? This is 8 plus 2.66, right. So this is the value over here, 8 plus 2.66 volts, which is 10.66 volts, right, because you remember the voltage that is actually seen at the load is 1 plus V gamma L times V1 plus. Okay, so there is sum of incident as well as reflected voltage, and that happens to be 8 plus 2.66, which starts at 0.3, and actually it would have continued like this, but unfortunately this minus 8 minus 2.66, which happens to be minus 10.66 volt, begins at 0.4, and therefore that would be 0. So in other words, this step response would have continued like this, okay, until the next reflection bit happens, but the step response, because of this negative input, would start and have an equal amplitude, thereby cancelling each other and leaving you with a pulse which again lasts only 0.1 nanosecond and begins and ends at 0.3 and 0.4 nanosecond with an amplitude of 10.66 volts. Now when does the next pulse arrive? The next pulse would arrive at 0.9 nanoseconds. At this point what would be the total, the value of this one? That would be minus 8 by 9 plus 8 by 27, actually this is in brackets, so you actually have 8 by 9 which is around less than 1, so if it was 9 then it would have been 1, so this is about 0.9 something, plus there is some other value that is here, so if you add them together what you get is about minus 1.18 volts, okay, so you will get minus 1.18 volt, and that would be negative here, right, so it would start at so this is 0.4, and then this would start at 0.6, and this is at 0.9 nanosecond, and then lasts at until 1 nanosecond, right. So this would start at 1 nanosecond, and this would have a value of minus 1.18 volt. So let me redraw that one over here just to clear up all the confusion. This pulse amplitude is 10.66, starts from 0.3, ends at 0.4. Then the next pulse, which is because of the reflection due to the mismatch between source transmission line and the other one, you are going to get another pulse at 0.9 nanosecond and lasting until 1 nanosecond, okay, and this value is minus 1.18 volt. next time you can actually calculate when you will get the next pulse, and that pulse would come at a later time, but it would have a small positive value, and again you will get a negative value, and eventually these transients would try to go to 0. I mean, they would go to 0 exactly at t equal to infinity, but if you wait for about 10 or 15 propagation delay times, then all the secondary pulses would go to 0. Now, one of the things which I want to emphasize here is that this kind of a situation is actually very bad. Okay, it's like one of the problems is that there are these secondary pulses. These after pulses are certainly not required. Okay, because if you want to launch not just one pulse but multiple pulses, then you have to wait until all these transients have died down. Otherwise, they would actually start to interfere. Okay, so because of these pulses that would interfere, your actual pulse output would not be the same as what your input is. So if the CMOS driver that you have connected is driving another CMOS driver, assuming that the load impedance and the source impedance can all be modeled as real resistive impedances, this kind of a situation with an interconnect delay that is quite large would limit the operating speed of the inverter and hence the operating speed of the overall circuit. Okay, something that you don't want to happen. On the other hand, which I will not do that one in this module, is that what happens when your transmission line delay is actually less than the pulse duration. Okay, so you can actually see that for yourself. I will not do this thing, but if you assume t is equal to 0.8 nanosecond, while the one step has gone and come back, the negative step is still has to begin. Like you see here, this is your diagram. So if we go up to 0.3 nanoseconds with the first step, right, the pulse itself now has to last all the way up to 0.8 nanoseconds. Okay, so this is 0.3. So the first step goes 0.3, then it will begin to come back and it would land here at 0.6 nanoseconds, right. So at 0.6 nanoseconds, the second step has not even begun to go, right. It's still all these points are going, right. So this is the first step point, then the next point would have gone, it would arrive here, the next one would go, next one would arrive. The negative step of value, whatever that initial value, I mean whatever the value, minus 8 volt, would not even begin to propagate until this 0.8 nanoseconds, right. So at 0.8 nanoseconds it would begin to propagate, but what would be the time it would take to arrive at here? 0.8 plus 0.3 is 1.1 nanosecond. So this is the time at which the initial pulse, which is lasting longer than the propagation delay, would take to arrive. Okay, here is where the cancellation starts to happen, but before that these guys would also come back. So 0.6 plus 0.3 would be 0.9, and again there is something else here. So the actual pulse output would look something like this. So initially you have a value of 8 plus whatever that 2.66, so that would be 10.66, and this 10.66 which begins at 0.3 nanoseconds would last until, so this is 0.3 nanosecond. Let me remove all the other lines that are not required. Okay, so sorry, I removed this line also. So you have 0.3 nanoseconds, this is 0.6 nanoseconds, and then 0.9 nanoseconds. So at 0.9 nanoseconds you will have, this is 10.66 because this is 8, this is 2.66, this is exactly the same things as we have calculated earlier, and this is minus 8 by, what is this value which we found, this is about minus 8 by 9, and then this fellow is minus 8 by 27. So at 0.9 nanoseconds you actually have to add up the values that are coming to you, minus 8 by 9 and minus 8.8 by 27, and that would be the value to which this fellow would have to decrease. Okay, so this decrease that would happen is actually about minus 8 by 27 plus 8 by 9. Okay, so this is the voltage to which this should decrease until you hit the next negative pulse, until you hit this 1.1 nanosecond where the negative step would begin to appear. Okay, so once the negative step begins to appear, you will actually see that this voltage, this is 948 volts. Okay, and this voltage is minus 1.18 volt, and this would be the way in which the pulse would propagate. In some sense this is much milder than what you have, but unfortunately the pulse duration has increased sufficiently, right. The original pulse actually lasted, the pulse duration is alright, but what would not be alright is this small distortion that would occur. Okay, of course the real problem with this one is that you are trying to actually limit the speed, because this is 0.8 nanosecond, so its frequency gets limited. You cannot drive many more pulses because the pulse duration itself is quite large compared to the propagation delay. Okay, so this is all that I would like to talk about the pulse response. Next we will look at what happens when there is a capacitive termination at the load, and we will begin from that one. Thank you.